Hi guys, welcome you all to this e-content. Today we are going to discuss about PN junction diode. So the objective of this PN junction diodes are we are going to describe the junction diode, how it is made, and we are going to define depletion region and barrier voltage, explain the difference between forward bias and reverse bias of a diode, and how to draw and label the schematic symbol for a diode, and how to describe the construction techniques of the diode, and next how to see the packages, common diode packages, and how to test the diode using a ohm meter. So this is the construction structure of a PN junction diode. We sandwich P and N type together to form a junction, and this is what you call it as PN junction. So in the case of P type semiconductor, the holes are the majority carriers and the electrons are minority carriers. Okay, these are electrons and these are holes. Here holes are the majority carriers and electrons are the minority carriers. While in the case of N-type semiconductor, the electrons are the minority carriers and holes are the minority carriers. Okay, so in N-type, the holes are the minority carriers and electrons are majority carriers. So now by itself, this P-type and N-type semiconductors acts like a resistor, but by doping one side of silicon crystal with the P-type impurity and the other side by the N-type impurity, we can convert the silicon crystal into the PN junction. And here this junction is the border where the P-type and N-type region meets. So this is the border where P-type and N-type region meets. And this silicon crystal with P and N-type impurity is also known as a diode. Okay, because where the P-type and N-type region acts like a two electrodes. So in this P-type region, each circled negative sign represents trivalent atom and a positive sign represents the hole. Okay, this positive sign represents a hole and this negative sign represents trivalent atom. Similarly, in the N-type region, each circled positive sign represents the pentavalent atom and each minus sign represents electron. This minus sign represents an electron. Okay. Now, due to doping, there is a large number of electrons on the N type but very few electrons in the P side. Because on the P side, the electrons are minority carriers, and whenever this P and N regions join, then the electrons from the N side starts diffusing towards the P side. The electrons from N type starts diffusing towards the P side. So whenever the electron enters the P type region, then it becomes the minority carrier, and being surrounded by the so many holes, its lifetime will be very short, and due to that it will be recombined with these holes. Okay, so whenever the electron diffuses across the junction, whenever this electron diffuses across this junction, then it creates two ions. So first, whenever it leaves this N-type region, then it leaves behind this pentavalent atom when it just one short of electrons. So due to that, it will become a positive ion, and whenever the electron enters the P-type region, then it will get recombined with the whole of this trivalent atom. So after capturing the electron, this trivalent atom will become a negative ion. So every time the electron diffuses to the P side from the N side, then it creates one positive and negative ion near the junction. Now these ions are the immobile ions, and unlike the free charge carriers like electrons and holes, they cannot move. So due to the recombination of these holes and electrons near this junction, there is hardly any free charge carriers near this junction. So or we can say that due to the recombination of this junction is depleted from free charge carriers, and due to that this region is also known as depletion region. Okay, so and this junction, a depletion region is formed because of the immobile charge carriers. Okay. So this depletion region is obtained. So this is the depletion region obtained because of immobile charge carriers. This depletion region contains both positive and negative ions which are immobile in nature. The ions present here will be immobile. Okay, and it is also contained a few charge carriers which are thermally generated in this depletion region. In this depletion region, these ions set up the electric field, and this electric field points from the positively charged ions towards the negatively charged ions. Okay, and only few electrons from the inside are able to cross this depletion region. From inside, a few electrons can able to cross the region, and the same is true for the holes in the p side region. So from p side the holes are difficult to move, and from the inside the electrons are difficult to move because of the immobile nature of the ions present near the junction. These immobile ions creates the barrier potential for this minority carriers, so that they are not able to diffuse from one side to another. From one side to another, they cannot. So this barrier potential is also known as built-in potential. So because of this immobile ions, the electrons present in n-type and holes present in p-type cannot move. So because of this, a barrier potential is developed, or barrier voltage is developed across the junction. We call it as barrier voltage. So here for silicon, this built-in potential or barrier potential is 0.7 volt, and for germanium it is roughly 0.3 volt. So the free charge carriers, hard to be precise, the majority carriers in both regions has to overcome this barrier potential to cross the depletion region. And only few majority carriers are able to cross this barrier whenever there is no external biasing. But due to this electric field, the minority carriers in both the regions will be able to cross this depletion region. Some minority carriers may move through this depletion region. For example, the holes which are minority carriers in the n-type region will be swept from n-type region to p-type region, and they will become majority carriers in the p-type region. Similarly, the electrons which are minority carriers in the p-type region will be swept due to the electric field in the n-type region. Once they enter this n-type region, they will become the majority carriers. So due to this built-in electric field, the majority carriers are not able to cross this junction. But still, the minority carriers will be able to go from one region to another. But when there is no external biasing in applied field, then the flow of electron due to this electric field and due to the diffusion will get cancelled out to each other. So the current in the circuit will be equal to 0. Okay, current in the circuit will be equal to 0. This is for unbiased condition. So this is not biased. Now it is an unbiased condition. If the majority carriers in both n side and p side wants to cross the depletion region, then they require some external biasing voltage. So based on this, we classify the biasing into two types. One is forward biasing, other one is reverse biasing. Okay, so in the case of forward biasing, here look at the picture. The positive terminal or p-type is connected to positive and n-type is connected to a negative. And in this forward bias condition, the external electric field is in the opposite direction to the built-in electric field, and due to that the effective electric field at the junction will reduce. So in the forward bias condition, the electrons in the n-type region and the holes in the p-type region will get pushed towards the junction. Okay, so due to that, the width of the depletion region will reduce. So if we further increase again and again the applied voltage or the forward bias voltage, then the width of the depletion region will further reduce. And when the applied voltage is more than the barrier potential of this PN junction, then the resistance that is offered by the depletion region is negligible from n side. In this condition, the electrons can cross the depletion region. They will get attracted towards the positive terminal of the battery. So once they come into the p side region, Then just by passing through the holes in the p-type region, they can reach the positive terminal of the battery. And similarly, the holes will be pushed towards the depletion region, and once they enter into the n side, then they will get attracted towards the negative terminal of the battery. So in this way we get a flow of current due to the movement of holes and electrons. As we increase the external applied voltage, the more and more electrons and holes will be able to cross the depletion region. Due to that, there will be flow of current. And now let me clear one thing. The hole is nothing but the absence of electron at a particular location. So whenever the electrons are moving from one place to another, hole is also moving from one place to another. So due to the movement of electrons, we also get the movement of holes. Similarly, let us see the reverse bias condition. See the reverse bias condition. The negative terminal of the battery is connected to p-type, and positive terminal of the battery is connected to n-type. In this condition, the electrons which are majority carriers in the n-type region will get attracted towards the positive terminal of the battery, and similarly the holes on the p side will be attracted towards the negative terminal of the battery. And due to that, the more the ions get created, so the positive ions will be attracted towards the negative terminal, and then the electrons will be attracted to the positive terminal of the battery. And due to that, more ions will get created near the junction. So here the ions, immobile ions, will be created near the junction. As we increase the reverse bias voltage, the width of the depletion, this junction region will get increased more and more, and due to that, now the depletion region offers more resistance to this majority carrier. So virtually there is no flow of current. In this case, the minority carriers in both the regions will be able to cross the depletion. So minority carriers in n-type and minority carriers in p-type will able to cross the depletion region. That is barrier. Here there is a barrier because of the depletion region, and attracted towards the negative terminal, and attracted towards the positive terminal. So in this way, in reverse bias condition, we will get a flow of current because of very less minority carriers. The magnitude, we cannot say there is no flow of current in reverse biasing, but there is a very less flow of current due to the minority carriers. This flow of current in reverse bias condition, we call it as reverse saturation current, which is in very micro amperes. Okay, here this is a schematic symbol of diode, two terminals, anode and cathode. Okay, and in forward bias condition, this is a circuit diagram of forward bias condition, PN junction diode. So diode is connected, the p-type is connected to the positive terminal of the battery, and n-type is connected to the negative terminal of the battery. So what happens is, during positive forward biasing condition, as the forward bias external applied voltage is increased more and more, the depletion region thickness will be reduced, and so there will be flow of currents because of the movement of holes and electrons. And similarly, when we see the circuit diagram of a reverse bias condition, so the p-type is connected to a positive, and the p-type is connected to negative, and n-type is connected to the positive terminal. So both are attracted, the opposite ions get attracted towards, and so that the depletion region thickness becomes more. So if the reverse bias applied voltage is increased because of the minority carriers in both the semiconductor, there will be a minority flow of current. So we cannot say the flow of current is nil, but there is still existing a small flow of current, a very less flow of current in reverse bias condition. And now this is the VA characteristics of the PN junction diode. So as we know, this is the forward bias. This is the forward bias condition, VA characteristic forward bias, and this is the reverse bias condition. And as the voltage, external applied voltage, get increased more and more, external voltage increased more and more, the current flow gets increased. So the graph linearly increases. And similarly during the reverse bias condition, so whenever we increase the reverse bias voltage, so at one point there will be a minority flow of charge carriers. Because of the minority charge carriers, there's a small reverse breakdown, and so that we call it as we have a small reverse bias condition. There's a small flow of very less flow of current. Okay, and this is a semiconductor construction, and this is a symbolic representation of p-n junction diode. And next, these are the construction techniques of p-n junction diode. This is grown junction, alloyed junction, and diffused junction. These are the varieties of p-n junction diode. This is a picture of diode packages, as I told in the objective. This is one diode packages of p-n junction diode. And how to test this p-n junction diode using ohmmeter is, ohmmeter can check the forward to reverse resistance ratio of the diode, and in forward bias diode the low resistance can be recorded using ohmmeter, and in reverse bias diode high resistance can be recorded in reverse bias diode. So finally, about p-n junction, once again let me define p-n junction, or let me explain in two lines about p-n junction diode. Is a p-n junction diode is a two terminal or two electrode semiconductor device which allows the electric current in only one direction while blocks the electric current in opposite or reverse direction. Okay, so finally the summary of whatever we have seen in this video was, we have created joining n-type and p-type materials together, sandwiched together. So we saw about the depletion region, we saw about the barrier voltage, we saw about the forward bias condition, we saw about the reverse bias condition, we saw about the diode packages, and finally we saw how an ohmmeter, what are the parameters the ohmmeter can detect in a p-n junction diode. Okay, so in the next video we will talk about the p-n junction breakdown in reverse bias condition. I hope the video you can understand what is p-n junction and how it can be operated in the forward and reverse bias condition. Thank you.